Hello, this is Andy Schweitzer, and I am going to give you a short video, sort of wrapping up in our classes some of the last concepts of equilibrium, and that is going to be Lechatellier's principle. Now, Lechatellier's principle, in a nutshell, says that if a reaction is at equilibrium, then it will, and a stress is applied, stress meaning that something has changed, then the reaction will shift to try to remove the stress or return back to its normal normal ratio of products to reactants. So let's go ahead and let's sort of review this concept here. So for this, I'm going to draw a little picture here, and let's imagine that I have a beaker, and this beaker contains two different chemicals. We're going to call it chemical circle and chemical square, and they are going back and forth between the two. Okay, and let's just say hypothetically that I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 circles here. Of course, this is not at equilibrium. We will be forming some sort of equilibrium ratio. I always draw this little gauge, and I'm going to say that this thing here forms it right down smack in the middle. So right now we are actually located right here. All right. So this thing will be going in this direction, right, as it approaches K. Currently we are at Q. Okay. Now, as it approaches this, we'll have some circles turning to squares, some squares turning to circles, but eventually we will come to a point where we will have lost some of our circles. And I'm going to eliminate randomly some of these. And let's go with these guys. I had 10 to begin with. And of course, if it's smack dab in the middle, we'll have, I'm going to use a different color here. We'll have 1, 2, 3, 4, and 5 squares. Okay, so this is a different color at this point. Okay, now we have now reached our equilibrium, and for this particular reaction at a specific temperature, we have a K that equals 5 squares. Sorry, 5 squares and 5 circles, and that ends up being K of 1. So no matter what, we're always going to eventually retain this balance of 1 as long as we maintain our temperature. So if I were to take this chemical reaction and give myself a little more room here, and let's just say I do something outrageous, let's add some more of something. Let's disturb this equilibrium mixture. I am going to add a bunch more, let's say, circles. Okay, so I got my black marker on here, and I'm going to add, let's just say, 10 more. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. 10 more circles. So now I've returned to this point here where I have reactants, products. I'm measuring the concentrations of these guys, and I had returned to this middle section where I was at K. Well, also I added a whole bunch more reactants in there that shoved me out of equilibrium, and I'm now got pushed back this way. I'm now at, again, what I would refer to as Q, some other non-equilibrium balance. Given time, again, circles will turn into squares, squares will turn back into circles, but eventually the circles will overtake the squares and we go back to our original K, which means going back to our original balance. It's not going to be 5 to 5, but the ratio will still equal 1. So, again, let's rebalance this thing. We'll lose a few more of my circles. 1, 2, 2 of them. I'll lose this one here. I've got 3 of them. I think this is right. Maybe use it one more. Okay, lost 5, and I will gain 5 of my squares. So I should have 1, 2, 3, 4, and 5. And unless I erased one too many circle, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we should have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 squares. So at this point, I have my K, and I'm going to click my marker there. I have my K is now going to equal 10 of my squares and 10 of my circles. Coming back to my balance of 1. So we just have to realize that regardless of what we do with this thing, it's going to come back to this K value. Okay? This is one example of adding a stress. Now I could have added things or I could remove things. That is our main type of stress, which is going to be, again, you could add, or you could technically remove. And no matter what this thing does, it's going to try and shift to compensate for whatever stress is applied. My next slide says, okay, let's show an actual chemical example of this, or rather I'll say a chemical reaction or chemical model. Let's go A plus B yields C. Let's just say A is a solid. Let's go aqueous, and let's go gas, okay? Keep in mind, because A is a solid, always looking for that, these aqueous and gas, the only two things eligible. So my K is going to equal to the concentration of, let's do in Kc at this point, of my C, and do the concentration of my B. And notice that, fortunately or unfortunately, this A doesn't even show up in this thing. So adding A, subtracting A will have no change, nothing affecting B or C's concentration. But if I were to, let's say, add B, okay? Now, there's two different ways in which they would maybe phrase this question. They might say, which way will the reaction shift? And I shouldn't have used, maybe I'm not going to use an arrow for this guy. I'm just going to use a colon, because or let's use a parentheses. All right. Which way will the reaction shift if we add B? Okay, now we have overloaded the bottom. We're now no longer at K, so we need to consume B, produce some C, okay, and therefore our reaction will be shifting to the right to counteract the addition of B. That means we will be losing some of these guys, gaining some of these. Will we lose some A? Yes. As long as A be lost, this will occur. Okay, now another way they might say, okay, they might track and say, okay, well, what is going to happen to C as we add a reaction? They may say, is C going to increase, or is C going to decrease by the addition of B? Well, most likely, for C to increase means we need to shift towards products. For C to decrease would mean we have to shift towards reactants. So in this case, they're not asking for which way you're going to shift. They're asking for how would that shift affect C. Well, addition of B is going to cause a shift to products, and therefore our C will increase. That's another way you could answer your problem. Okay. So addition or removal of products, pretty common question to be asked for Lechatellier's principle. There are other things here. This one says, other types of stress, what if we add or remove an inert substance? Okay, inert meaning it's not doing anything in our reaction. A plus B yields C. Solid, aqueous, and gaseous. What if we add D? Okay, again, my Kc equals the concentration of C, concentration of B, and A is not in there, but neither is D. So in this case, D is going to have no effect on the concentrations of C or B, and therefore will not have any effect on the chemical reaction. Okay. The next topic we might have, okay, what if we add a catalyst? Now, again, this little drawing, we have reactants going to products, we have our K value, okay, and the question is here is a little bit different question, but basically it's saying if we're not at equilibrium and we have Q, and we have K, and we're going to be moving towards K. How is a catalyst going to affect the ratios of my product concentrations versus my reactant concentrations? And the answer is no effect. Only thing a catalyst is going to do is decrease the amount of time it takes to get to K. Very important. It's not going to affect my actual concentrations of products, concentrations of reactants when I get to equilibrium. It's just going to shorten the amount of time it takes to get there. All right. What if we reduce or increase the volume of a substance? Now, this is sometimes linked to pressure. So pressure and volume are sometimes linked. For example, if we're dealing with a rigid container, and let's say I have a reaction A plus B yields C. Okay, now I have, this is marked as a solid, this is marked as an aqueous, okay, this is marked as a gas. Okay, solid, aqueous, gas. Kind of hard to see with these markers, but so in reality, I have maybe have a little liquid here, and I have some B inside here, floating around. Okay, and then I have above it, I have some C's floating above it. Okay, so now I could, by chance, okay, plug in more C into this reaction. Okay, now the way you would phrase that is, I'm going to increase, okay, my pressure by adding C, okay, which is fine. All I've done in this case is my K C equals the concentration of my C, concentration of my B. I have essentially added more C, so my reaction will shift towards the reactants as a response to this guy kind of getting cranked up in pressure. It will try to undo that. Okay. There is, however, another way in which I could hypothetically increase my concentration of C, and that's by reducing the volume. So I could take this same picture here. Let's draw another one here. All right, and let's just say I take my problem here, and I'm just going to kind of mimic this a little bit. All right, I have my beaker. I have a little bit of B floating around in here. I also would have A is going to be there as well. It's a solid. Maybe it's even on the bottom here. And I have some C's in the container here. But instead, I'd have a piston. That's usually how they phrase this, a piston type situation. And this piston drops and removes and squeezes these guys into a smaller volume. Now again, we're measuring the concentration of these guys. I haven't changed the concentration of the B's. It's still the same volume, same number of particles, so that hasn't changed. But C, however, has the same number of moles, but it's in a smaller volume. That's going to increase my concentration of my C. And if we were checking partial pressures, okay, the pressure of C is determined by the PV equals nRT. So the pressure is equal to nRT over V. By dropping the volume, I can cranking the pressure up. So in this case, I am definitely going to be increasing my concentration, and once again, it will cause this reaction to shift to the left because I am ramping this value up. Okay, I would be losing C, gaining B, and I would also be gaining A, although it is a solid. A very common problem that they might add in here is, okay, what if we have this beaker here? And I'll just draw the same beaker again, and I have some B here and some solid here, and I have, let's just say it's closed. Okay, so I have some A right here, and I'm going to insert this thing in some D. And they say, okay, I'm going to increase pressure, okay, by adding some D. Now granted, the total pressure of the entire container, PV, nRT has definitely increased. But if you look at the partial pressure of just A, P V equals nRT, it's going to be the pressure equals nRT over V. Does the same number of A's exist? Yes. R is the same, temperature is the same volume? Yes. So technically, the partial pressure of A has not changed. Partial pressure of A is constant, and therefore this would have no effect. Okay? The last thing we're looking at here is quite simple, and that is going to be, what if we're adding and removing temperature? So let's say we have A plus B yields C. Let's say this reaction happens to be exothermic. I could show that in two ways. Delta H equals a negative X, and by the fact that it being negative means it's exothermic, and I'd have energy on the product side. Or I could have A plus B yields C, and delta H equals positive X, in which case it is going to be endothermic, and reaction energy goes on this side. So our two options are problems that we could simply say, I'm going to either add energy or remove energy. This is the same thing as saying increasing the temperature or decreasing the temperature. Now, for this example, if I were to add energy or raise the temperature, it would shift in this direction, okay? So if I increase the temperature, this is the way it shifts, away from the energy. If I were to lower the temperature, then it would shift in this direction. This guy would be just the opposite. I'll make one more quick point before I end this video, is that of all of these stresses applied, this is the only one that actually changes K. Now let's just take this example right here. If I were to increase my temperature, then I would be shifting in this direction. Now keep in mind, my concentrations would be losing A and B and gaining C. So if I was at equilibrium before and these concentrations were static, by any temperature I'm losing and gaining. So I have to be no longer at the old equilibrium I was at. I'm at a new equilibrium, new conditions. So I would be gaining more C, losing this. So in this case, my K is equal to ratio of concentrations of my products over concentration of my reactants. And since I'm gaining more product, losing reactants, my K is going to be increasing in this case. If it went the other way, due to a temperature shift, I would have less product, more reactant, and my K would be getting smaller. Something to think about. Thank you very much.